Good afternoon, everybody. Thank you for being here. This is one more session of the QRC seminar. Thanks also the experimentalists for coming from the lab. Before I start the introduction of Alex, our invited speaker today, I also want to make an announcement that this week we have an extra speaker. This is Professor Thomas Busch, who's sitting there. And it happened that we have two very good speakers in the same week, and in fact in the same couple of days. So tomorrow at 5, we will have another session with Thomas, just for you to know. They asked me to accommodate him into the QRC seminar on Monday, but this was already taken. That's why we're having an extra seminar tomorrow. So then let me now introduce Professor Alex Retzker from the Hebrew University of Jerusalem in Israel. This is a very special invitee from my side, in a sense. I met Alex long ago in a very nice school. I think it was in 2005 in Dresden, in the Max Planck Institute of Complex Systems in Dresden. And that was a very interesting school. We were like 5 or 6 weeks together, all students there, staying together in a guest house and doing lots of party, but also doing lots of science. And it's interesting, most of the people in that school are nowadays faculties in interesting positions in the field. Most of them have not left the field, right? Then I've been meeting Alex Retzker over the years, but this goes back to those years as students in Dresden, in Germany. So let me make a brief introduction. Alex did his PhD with Benny Resnick in Tel Aviv. He was then postdoc in the group of Martin Plenny when he was in London in Imperial College. And then in 2012, he moved back to Israel, where he kind of rejoined the Hebrew University of Jerusalem, and he's now full professor there. He's also part of the research effort in AWS and in quantum, in the Amazon Web Service quantum, right? He's working closely with Oscar Painter there. And I should also mention that he's co-founder of one startup in Israel. This is called Envision, and it's for sensing applications, more focused to medicine applications and other things. He's also interested in quantum sensing. So Alex is one of those theorists that understands deeply experiments too, and it's great to have you here. Alex, thanks for coming, and please, and by the way, is it okay if we ask you questions during the talk?
Yeah, sure.
Great, okay, thank you so much.
Thank you, Leandro. Thanks for the very nice introduction and for inviting me here. I will talk about Erasure qubits. It's a way to overcome the T1 limit in superconducting circuits and also in our systems. It's a work, part of my work in AWS, in Amazon, and it's a work in collaboration with Alex Kubica, Arbel Chaim, Yotam Vaknin, and Fernando Branda. So I will talk about ways to overcome the T1 limit, and the T1 limit is a fundamental limit for gate fidelities in all actually quantum computing architectures and all platforms. And so basically it creates a fundamental limit on the infidelity, which is T gate divided by twice T1. So because of, in some cases, the short T1, the infidelity basically is limited by that quantity. And T1 is usually, and the reason that it's a kind of fundamental limit that you can't overcome by various methods, because it basically originates from short time scales for high frequency reasons, for high frequency elements. And T1 means basically if we have a 2-level system or a higher level system, suppose here a ground and excited, and some level broadening of gamma E, it means that after time, which is 1 over gamma, the system will decay from excited to ground. And the reason it's kind of fundamental because the typical time scale of this, the decay can be long, but the typical time scale, the correlation time of the noise is on the order of the energy gap, and the energy gap is usually quite high. Mathematically, we can write it in Krauss representation, which is a mixture of two processes. One is the decay from 0 to 1. So here, actually, I write 0 and 1, another ground excited, so this will be 0, this will be 1. So one is the decay from 0 to 1. The other one is a dephasing between 0 and 1. So in case there is no decay, there is still a difference, imbalance in the population, because we still get information even if there's no decay. So this is in a discrete way in terms of Krauss operators. We can also write this in a continuous way in a master equation. And again, it's a mixture of two processes. One is the decay from excited to ground, which is this term, and the other term is the dephasing. Dephasing between ground and excited. Again, please feel free to ask questions during the talk. And again, this noise is very fundamental in sense kind of the limit to infidelity. And because of this, there was, and now there still is, a very intense effort to increase T1, basically by material science, by improving the material science of the fabrication, and also by kind of trying to by the design, so there is less coupling, there is less noise at high frequency. And it was a very successful effort. So T1 is prolonging extremely rapidly, relatively rapidly in the field of superconducting circuits, also in other systems. And that's kind of very fundamental.
Am I right?
Yes, here it's 1 over this gamma. So it's, sorry, 1 over this gamma. Yeah. And so this is the continuous process.
Mm-hmm.
The definition of T1 is 1 over this gamma that gives the time scale. The small gamma here is for the discrete process that depends how we define it. Usually it's gamma delta, it's gamma delta T.
And this is the amplitude damping model, right?
That's amplitude, yeah.
Okay.
That's also
Thanks.
amplitude damping. Yeah,
Right.
that's true.
Right. Thanks.
But on top of T1, there's also phase noise. And phase noise is basically means if we have a two-level system, so there is some kind of noise that dephases the system. So basically this state kind of jitters and creates some kind of uncertainty in the frequency. And it means if we put the system in a superposition of down and up, it will get, of course, if we have the energy gap between down and up, it can be in some interaction picture, but also there's going to be some f of t, some kind of noisy element, some kind of stochastic element. And this will cause the oscillations of the coherence. Instead of oscillating for a very long time, it will create a decay. And that's also a fundamental, it's also a limit on the infidelity, but kind of less fundamental, because this one can be prolonged in some cases by dynamical decoupling. Usually the time scale, the correlation time of this noise is not so short. The correlation time can be long, and because of this, if we dynamical decoupling or drive the system faster than this correlation time, this can be prolonged. And how it can be prolonged, and there is a nice overlap formula, that the overlap between the oscillations, the drive, the control, and the power spectrum. Basically, it means if this is the power spectrum of the noise, it's usually the power spectrum is a decaying function of omega. It basically means if we don't do anything, that the noise at low frequency kills us, which is very high. But if we drive the system very fast, suppose we drive it, we take the system and we drive it, then suppose at this frequency here, suppose in this units of 2, so only the noise at this frequency can do something to us, can harm us. And if we drive it even faster, then only the noise in this frequency can harm us. And because usually power spectrum is a decaying function of frequency, so the stronger we drive, the weaker the power spectrum, the noise that actually harms us, and the longer is the coherence. And this is basically the main idea behind dynamical. Yes, that's an echo effect. That's exactly an echo effect. And the echo effect works up to some limit. And the limit is the power spectrum at the frequency of the echo. And because usually the correlation time of this noise, of phase noise, can be long, it's possible to echo it to some sort of extent. Well, you can just drive it as fast as you want and see what happens. If you know, it's better.
So Alex, here, this is an ignorant question. So here, when you say driving, you resonantly drive it, or so?
Yes.
Okay.
Yes. Usually,
so
usually resonantly driving, as strong as possible. Yeah.
And so what you're saying is like a fast pulse, essentially, right? Okay.
Yes, or continuous or pulses, yes, whatever you can do.
Okay.
Okay. Okay, so there is, but now T1 also sets a limit on the coherence time in a way. So if we say that the infidelity is limited by T gate divided by T1, this is the T1 limit, but there's also T phi. So the T phi, how we define it is what is left after T1. So this is the phase noise that is left after T1. So T2, the coherence time, would be a combination of both. And this would be T phi. So if you look at the coherence time, which is combination of both, we cannot change T1. For this, we have to drive extremely fast, which we can do. But we can actually increase T phi quite a lot. But again, T2 is limited by those. So T2, if T phi is very long, T2 will not change so much. And the question is, can we, if we go and increase T phi by dynamical decoupling, can we do it? Can we somehow construct a gate scheme or a fault-tolerant scheme in which the gate is limited not by T2, but by T phi? And because T phi can be very long, then we can gain a lot. So that's the question. So naively, you would say, no, you can't, because T2 limits you, not T phi. And if T phi is, yeah, so T2 is basically, if you look at the coherence, that's what happens. And if T1 is very short, then T2 is limited by twice T1. T phi is what happens due to the phase noise. So suppose if you have like, I don't know, T2 of a microsecond and your T phi is very long, it can happen that there's no phase noise for some reason because it's only limited by T1. You can think about a scenario like this. T2 will still going to be limited by this microsecond, even if T phi is an hour. Okay? So there could be a big difference between them. So T2 can be still very short and T phi can be very long. And in principle, you would think T phi is kind of meaningless here. Only T2 limits you and T gate is limited by T2, which in some cases can be very short. And the question is, can we kind of design some kind of scheme in which what will limit us would be T phi and not T2? Okay? And naively you would say, no, you can't, because T2 is what you have, T2 is what you measure. T phi is kind of a very low SNR, kind of benchmark of something which is kind of even irrelevant for quantum computation. And the question, can we design some kind of scheme in which what will limit us will be T phi and not T2? And T phi can be much longer. Yeah, should be T gate divided by T2, which is limited by T1. This way, the infidelity is always limited by this quantity. Yeah. So in principle, it's T gate divided by 2T2. Yeah, that's true. It can be due to the phase noise, which is still noisy, but it's not because of T1.
Yeah, like
no, it can be noisy. So I mean, each time you run it, it's a different noise. So if you average over, the superposition is there. Yeah, so infidelity is, it's right, this T gate divided by 2T2, which is limited by T1. Can we somehow create some kind of scheme in which it's not T1, but T gate divided by 2T phi, by T phi, sorry, by T phi, not T phi. Now, if you look at experiments, so this T phi is not measured so much because it's not considered as an interesting quantity. There's not much you can do with it. So people didn't study it so much. But in these two papers here, we can see one from the group of Bylander, the other one of the group from the group of Will Oliver. What you see here, this is like measurements of T1, this black dot, this black line, which is on the order of tens of microseconds. But when they measure T phi, they reach, it's around the millisecond. Yeah, so it's more than one order of magnitude difference. In this paper here, they just measure T1 and they just measure T2. So this is like it's a statistical measurement. So those things are fluctuating. This is T1, this is T2, and T2 is longer than 2T1. It's not supposed to be, but because of fluctuations, you can get it. But in principle, if it means that T2 is extremely close to 2T1, it means that T phi is very, very low. At least more than order of magnitude longer. So in these experiments, there's not so many experiments because T phi is not such an interesting quantity. It's not considered to be interesting. But we can see that T phi is more than, in many experiments, T phi is more than an order of magnitude longer than T1. So maybe we can do something. So the question is, yes, if infidelity is limited by that, can we somehow construct a scheme in which the infidelity would be limited by T gate divided by T phi? And so how do we can think about it in the following way. We can think that T1 is a very special kind of noise. It's a noise we can deal with it in an efficient manner. We don't have to use the full power of error correction to deal with T1. So if we do that, we kind of deal with T1 with kind of a simple code or kind of in a simple way, then what is going to be left is T phi. Okay. So what we can think of that first, we kind of do dynamical decoupling. We increase T phi as long as we can. We increase it a lot. Then we kind of have a very simple code that kind of eliminates T1. And what we are left is suddenly T phi. Okay? So we don't have to use all of error correction. We can use a very simple code and then increase T2 to T phi and then put it in a surface code and use it. And why do we know in principle it's possible? Because we know that if you want to do error correction, we want to kind of correct any error there is, the minimal code is a 5-qubit code. And even that is not extendable to fault tolerance and all, but still this is the minimal code. But we know that T1 is possible to correct with 4 qubits. And because of this, we know that T1 is a simpler error to correct than a general error. And this is called the 4-qubit code, which was introduced by these authors. And the idea is kind of simple. Suppose we look at this encoding when this is the 0 logical and this is the logical 1. Suppose there is a decay in the first qubit. So if there is a decay, this state decays to 0, 1, 1, 1. This state decays to 0, 1, 0, 0. So it decays to this superposition. These two states are orthogonal to one another, but also orthogonal to all the logical ones because there was one excitation, so it has to be orthogonal. So in principle, we can correct it and continue the computation. That's the idea. There's also dephasing, and this can be, but dephasing is of second order, so it can be correct. That's what it's called. No. So suppose I start with alpha logical 0 plus beta logical 1. And then the first qubit on the first qubit of this 4, there is an amplitude damping error. So this one, first it just measures this out of that because there's no excitation here. And this one becomes a 0. So all this 0 logical becomes 0, 1, 1, 1. Okay? Project out the first. Well, the amplitude damping projected for you, right? And this one goes to 0, 1, 0, 0. And we can create a unitary mapping that maps the 0, 1, 1, 1 to 0 logical and to 0, 1, 0, 0 to 1 logical.
Yeah. So when you say that amplitude damping projected, you're kind of assuming that someone detected a photon.
Yes, okay.
How like the path is acting, you apply the cross operators of amplitude damping first get, it stays invariant. It's not projected out. Not sure.
If I apply,
you know that someone detected a photon, and you're sure it was the second point.
So if I apply this cross operator, that's what I get.
Yeah.
And the reason that I can know that, is because I can make a projective measurement on the number of excitations. The number of excitations here is odd, and then is even, and the number of excitation here is odd, so I can do it without projecting the state, and I can know.
But this cross operator you mentioned,
yeah.
By the entire map.
No, that's correct. But now I can make a measurement, a projective measurement on the number of excitations. And if I make a projective measurement on the number of excitations, I know that K1 has happened and not K0, because the number of excitation here is odd, and here it's even. Okay? And this way I can know. Yes. You're right. That's true. And the measurement on the parity of the excitations, if it's even or odd, gave me back the purity. Yeah. The cross operator takes away the purity, but the measurement gives me back the purity. That's right.
I mean, for the things that it's correct.
So I measure only if it's the number of excitation is even or odd. I don't measure the number of excitation. Okay, so what do we learn from this example that was done by these authors? That T1 error is still kind of a simpler error to deal with than a general error. So if we know that the fundamental limit or infidelity is T1 and not a general error, maybe there is a simpler way to deal with this, to give us a better fault-tolerance threshold than the regular, suppose, surface code. Okay, there's another kind of, there are some versions to this, to the 4-qubit code. Another version which I prefer usually to work with is this encoding 0, 0, plus, minus, 1, 1. And then the 0 is plus, plus, 1 is minus, minus. It's more of a symmetric code. It's easier to work with this and understand what's going on. It also kind of behaves better with the phase. But the original encoding was this one. Okay, so what can we do in principle? We can take, so this is kind of an example of a surface code. Each dot here is a qubit. Each rectangle here is a measurement. So these ones are measurements of ZZZ and this one of XXX, or the other way around, I forget. But yeah, so we just we can make parity measurements of these plaquettes. And in this way, the surface code works. And what we can do, instead of each node here, we can put a 4-qubit code. And then we have to make gates between these 4-qubit codes. But the 4-qubit code basically deals with T1. So T1 is not important anymore. And what limits the surface code is T5. So now the threshold of the surface code, instead of being a T gate divided by 2T1, it's only T gate by T5. And suddenly the infidelity is kind of reduced by an order of magnitude, maybe even 2 orders of magnitude. Okay. That, yeah, so I kind of, yeah, I increase the T1 or even get rid of it entirely. And now I'm limited only by T5. And because T5 is much longer than T1, I can gain quite a lot. Okay. So this will be kind of a naive idea, but it doesn't work. The reason it doesn't work, maybe I have 2 explanations. One is more intuitive. Maybe so much time do I have? Maybe actually I'll skip to this one. The reason it doesn't work is that for the T1 limit, so which is a decay from excited to ground, the reason that T1 error is easy to deal with is because there is a clear asymmetry. The decay is always from excited to ground. But when we add dynamical decoupling, when we start rotating the system, suddenly what happens is that this asymmetry is gone. There is a complete symmetry. And what dynamical decoupling does, it takes the T1 error and transform it to a general Pauli error. So we cannot use this simple code anymore. So we worked this quite a lot, but we never managed to find a way to do that. So basically this rotation kind of breaks the asymmetry between excited and ground. There is a symmetry again, and the noise becomes a worse noise. So the 4-qubit code doesn't work anymore. So it's not kind of compatible with dynamical decoupling. And because T5 is only longer than T1 if you use dynamical decoupling, we have a problem. But maybe we can use something else. Maybe we can use erasure. Maybe we somehow can detect the T1 in kind of a physical way, in a different way than making projective measurements. And in this way, we can increase the fault-tolerance threshold. I'll show you a few examples. Suppose in this 4-qubit code that I prefer to write it like this in plus and minus, if there is a decay of the first qubit, then this 0, 0 plus 1, 1 becomes a 0, 1. So again, this thing is projected and to here, and we have a 0, 1. Again, we can make projective measurements. We can make this projective measurement is it what is the number of stages? Is it even or odd? And because of this, we don't have it. But this projective measurement of even or odd is a complicated measurement. It requires for us to do many gates. If we can measure it somehow differently, we don't have to make all these measurements, and actually we can make the correction. If we know that the first qubit has decayed, we can just instantly make the correction. We don't have to do any measurements whatsoever. And of course, that simplifies things a lot. If you go back like for the Shor code, for the it's canonical example of the Shor code, right? The Shor code is a 9-qubit code, and we have to measure these operators, this XXXX 6 times, or we have to measure the ZZs. We have to measure all these operators, and we can correct. Yeah. So the Shor code basically has either a bit flip or a phase flip. And if you measure all this, so here an example when there was a phase flip, suppose on the first qubit, the plus becomes a minus and the minus becomes a plus, or they can also be a bit flip. In this example on the first qubit, how do we detect it? We make all these measurements of this, we make of the ZZ operators of the XXXXXX. We make measurements of these operators and we can correct. Now, but what if it's an erasure? If somehow we know that the error happened on the first qubit, we don't know which kind of error exactly, but we know that an error happened on the first qubit, then it's much easier for us to correct. We only have to measure the first 3 qubits. We only have to measure XXX or ZZ of the first 3 or 2 qubits. We don't have to measure all the other ones. So we have much less measurements to do. And because of this, the fault-tolerance threshold here is going to be much higher. And the same thing works for the surface code. So the way it works in the surface codes, so in this example, this red stars, it's when we made the measurement and we got the wrong parity. We got the odd parity, but now we have to correct. And the way we correct in the surface code, we kind of find the shortest way to correct, either from here or from here. And actually, the shortest way to correct is via the edges, which means here is Z1, Z2 operation. But actually, suppose these errors were erasures, and we know that the errors happens in 2, 3, 5. So we know actually we have to correct these ones and make a Z2, Z3, Z4 operation in order to correct and not this one. So the fact that even in the surface code, if we know where the error happened, it also helps us quite a lot, and we can make the correction in a better way.
Sure. So you just know where the error happened, but it's not the erasure channel that removes the particle away, right? Like in photonic systems, right?
Yeah, it means that I know that that the error happened in which.
Okay. Because there is something called the erasure channel, and people develop error correcting codes also for kind of losing a particle for photonic states, right? But
but they know which particle is, so that's why that's why the name stuck also for these errors.
Okay, I don't remember like this.
Yeah,
okay, but so here essentially the important thing is you know where the error happened, and this simplifies the correction, but also the encoding itself, in terms of number of qubits or not.
So usually it's yeah, in principle, probably you can even do something better, but it requires already kind of a different code, and it's we don't. It's very difficult. We don't know how to improve the surface code, but so this is only for the correction. In principle, yeah, there is a potential to do it even better, but this we don't know how to do. Okay, so how do we design an erasure measurement? One thing is the superconducting, there's also a third level. There's more, but there's also a third level. So we can use this one for computation. So suppose we kind of design a 2-photon process, kind of detune from the excited to drive it from 0 to 1. And if there is a decay, it decays to the excited. So the 1 decays to the excited. So actually we can think about the rest states, which are the ground plus minus F. And if there is the decay, it's just that the 2 rest states, they decay to the excited. If you can measure if it's in the excited or not, we know without decohering 0 and 1, if we can do that, then we converted the error to an erasure error because we know that the error has happened and we know in which case. And then T1 becomes an erasure error and the T2 becomes T5. And this driving between this 2-photon drive between the ground state, and the F state actually is already dynamical decoupling. So it kind of creates the dynamical decoupling, it increases T phi a lot, and we have and we converted the T1 error to an erasure error. Yes, so that's true. So I'm driving, but I'm driving from 0 to 1 without occupying the excited state, or I'm occupying it very weakly. So there is a small chance that there was a decay from excited to ground, but most chances are if there was a decay was from F to excited. And from excited to ground, but okay, so the two photon process, it's a two photon process driving. The population of being in the excited is omega square, typical omega, divided by the detuning square. So it can be very small, maybe percent, maybe a few percent. So whenever there is a decay, we know that it mostly was from F to excited, and with some percent or a few percent chance, it was from excited to ground, and we just live with that. Yeah, so if the erasure, if the chance for erasure is kind of small, it's a percent, and this one is percent, so we end up with 10 to the minus 4, and we just live with the 10 to the minus. That's true. That's true. Yeah. That's true. So this is one way. The other way is to use a dual RL, which is an idea that was in principle developed for spin qubits in solids, and also used in an experiment by the group of Will Oliver. And the idea is to couple two transmons capacitively. And if we couple them capacitively, it just couples excited ground with ground excited, so it has two eigenstates, ground excited plus or minus excited ground. So and if we use this as a qubit, whenever there is a decay, the decay is from these states only to the ground. And this experiment was done by the group of Will Oliver. Here, these are like 4 transmons. In each couple of transmons, these two and these two, they kind of constitute this dual RL qubit. So again, if you take like 2 qubits, we couple them, and if we diagonalize the system, we have 2 eigenstates, 1, 0, minus 0, 1, and 1, 0, plus 0, 1. There is a gap between them. This gap, which is the coupling, actually is kind of dynamical decoupling. The capacitive coupling itself creates dynamical decoupling because only noise at omega 0 can make a transfer between minus and plus and kind of limit T phi. And T1 is a decay from these 2 states to 0, 0. So if you can somehow make a projective measurement, is it in plus or minus, without asking the question, is it in which state it is, or is it 0, 0, we can detect erasure without decohering the qubit. And in principle, if the coherence time, the correlation time of the noise is long enough, we increase T phi from T phi of the transmon to this T phi of the dual RL by a factor of omega 0, the strength of the coupling T phi transmon. So if we can plug here this, so the capacitive coupling can be very strong, like 100 megahertz. T phi transmon can be on the order of 100 microseconds. And then in principle, we can get improvement of 10 to the 4. So it can potentially, it's a very, very long, very large improvement. Also, an order of magnitude, the third order of magnitude will be actually great because it means that the infidelity is reduced by a factor of order of magnitude. But in principle, there is a large potential even to get to 4 orders of magnitude. We can also do gates in this setting, which always live in this protected subspace. We can just take these 2 double transmons, these 2 DORS, couple them dispersively at high detuning. And what they get effectively is a coupling, which is an XX, which is a ZZ coupling, or in this case is an XX coupling. So what we get is a coupling, kind of a dispersive coupling of 2 transmons, which is XX. plus the 2Z operations, then gives us an exchange of energy. If these two transmons are on resonance, if the coupling between them, if this gap is the same, they just can exchange interactions, these effective interactions. So when they're on resonance, these two dual constructions, they can exchange interactions. And that's an exchange of interaction gives us a nice swap, which if we actually add another pulse in the middle, gives us a C phase, which is exactly what we need for error correction for surface code realization. How much time do we have?
2 and 3.
Yes, so 1 and 2, suppose in this example here, in this work of the group of Oliver and MIT, 1 and 2 is one dual rel, 3 and 4 is another dual rel, and 3 and 4 are coupled with G1. Yeah. And if it's off resonant, if you do it off resonantly, then you can get exchange of these effective interactions of so we can think about this, we have these two dual rel. If they are resonant, they should exchange interaction. An exchange of interaction, when it's on resonance, that gives us a gate which is called I swap, which is easy to convert to C phase by just a one pulse in the middle, which we have to do anyway because it creates an echo. So it's always good to add a pulse in the middle. It also gives us an echo. So basically, an I swap immediately gives us a C phase. We can also think about this gate. So I don't have much time, so maybe I'll skip this part, which explains the gate.
But you mentioned that you need to be able to measure the 0, 0, right? To distinguish that from the intermediate state,
So
right?
this is what I'm.
Okay, okay, yeah, thanks.
Okay, so if we go back to a single dual rel, we have to distinguish the minus and the plus somehow. Sorry, we have to distinguish the minus plus subspace from the 0. So how do we do it? In principle, it's kind of tricky because whenever you measure something, you just dephase it, so it kind of doesn't sound so good. But the idea would be the following. So suppose we have the two transmons. Now we couple, usually in superconducting qubits, the way we measure transmons is by coupling them to a readout resonance. Now suppose we couple both qubits, both transmons of this. So this is one qubit, one dual qubit. Suppose we couple both transmons to the same readout resonators with more or less the same coupling strength, more or less the same capacitive coupling. So what happens now is that it's like a decoherence-free subspace because the resonator cannot distinguish between 0, 1, and 1, 0. It thinks the same. There's no way the resonator can distinguish between them. And if it can't distinguish between them, then it will not decohere the system. But it can still measure the number of excitations. So it will still dephase or distinguish between 0, it will still distinguish between, it can calculate the number of excitations. So it still measure between this subspace and this, but it will not decohere these ones because it doesn't distinguish between 0, 1 or 1, 0 or any superposition between. Okay? Right? Just by this construction, the readout resonator has no idea what is excited, this one or this one. It's the same thing. Okay? It's a complete symmetry.
Sorry, you want to, ideally you would like to project the 0, 0 out. 0, 0 is not decay.
No, I just want to measure. I just want to measure, is my qubit here or here? The decay happened because of the decay, if it happened. I just want to find if the decay happened. Did it decay from here to 0, 0? That's the question that I'm asking. No. So no, because in this measurement, I mean, I can show you the Hamiltonian, but just by this, if GRT1 equals GRT2, the readout resonator doesn't know if the excitation is 0 here. This is the same. There's no difference, completely symmetric to this. So it cannot distinguish between 0, 1, and 1, 0. So it cannot distinguish between the minus superposition and the plus one. There's no way it can do it. Okay? Of course, it's not going to be the same. There's always going to be imperfections. And we show that even if even if it's like 10% of imperfections, it still gives us a very good measurement. Okay? But in principle, if we do it this way, we cannot decohere the qubit, but we definitely can measure if it's in this state or one of these states. Okay? Then we can write the Hamiltonian of the measurement, and the Hamiltonian shows that both plus and minus are coupled to the readout resonator with the same coupling if they are equal. And if they're not equal, if GR1 is not equal to GR2, there is kind of term which is not so good, which can cause us problems. And we analyze it and we see that even 10% doesn't cause us too many problems. And 10% imperfections in capacitance is not big restriction. Okay, so what do we do now? So we take the surface code, and each point in the surface code we put either this tree-level system or we put the dual rail, and now we do everything with that. So yeah, and then we do gates between the dual rails actually, and now we analyze the system, and that's what we get. So what we see here is like the analysis of the. Yeah, and the surface code is spelled. Okay, so now we can look at this graph. What it means, it's kind of analysis of the surface code. If you remember, just remind that the surface code behaves in this way. If this is the regular surface code, if this is the probability for a Pauli error P, there is kind of P threshold, and it improves with the distance of the code. So D is the distance of the code. This square is the number of physical qubit in a logical qubit. And there is this 10% point, which if we are exactly at the threshold, we still get 10% infidelity. What we see here, this is the axis of the Pauli error. And this should be our like T phi error. This is the axis of the erasure error. And every point here is the analysis of the surface code. So what you see here is a Pauli error, is the physical error, and this is the logical error. So if the physical error is higher than some threshold, and this is the distance. So this is like distance 5, this is 7, this is 9, and this is 11. So if the Pauli error is higher than some threshold, so if we go and increase the qubit, things actually becomes worse. Yeah, there's no point of doing that. If the Pauli error, if our error is below this threshold, so if we go and increase the logical qubit, things become better. Okay? So and this is the threshold. Yeah, so we have to go to be below the threshold. And each point here is analysis of this. So this is what you see here. This is the regular. This is the regular. This regular scheme. It doesn't take into account of erasure. So erasure and the Pauli error is the same. There is some. Yeah. So all this area here is a good area. Whatever here is a bad area. So yeah. So basically, the regular scheme cannot distinguish between T1 and T5. So T1 is just T2. So there is asymmetry here. This is because of the definition of the Pauli error, because the way it's defined in the surface code to get this formula is that P is the Pauli error, but also P reflects the measurement error and all the other errors. So there's kind of 2/3 coefficient. I don't remember exactly. Okay, but if we take into account the scheme that takes into account the erasures and does the corrections accordingly, then suddenly the good area becomes much better. So it means that, so suppose the probability of erasure is 1%. Yeah, 1%, in principle, if you're using the regular surface code, 1% is already above the threshold. So there's nothing we can do. We can see that with 1%, we are still fine. 1%, we can still leave, the error becomes, it's not 0.007, it's not 0.7%, maybe it's a bit less than 0.6, but it's not such a big difference, but we're still in a good region. Yeah, we can still, and the cutoff is 5%. So the erasure gives us quite a lot of advantage. So what we see here, it's another analysis of this. So what we see here, suppose this one here, it's E. So E, it's like there's no erasure and there's only 0.1% of error, of Pauli error. And it decays with the distance quite a lot, right? Because 0.1% is below the threshold. The threshold is 0.7%. So if we are at 0.1%, then the logical error rate reduces quite well with the distance. If we have 0.1% of Pauli error and 0.6% of erasure error, this is B here. So basically, there's no improvement. There is a slight improvement again because the definition of P in the Pauli error also induces other errors. So there is kind of tiny improvement. But in principle, the sum of those is 0.7%, which is exactly the threshold, and there's no improvement with the distance. Okay? Again, it goes down a bit because of this definition of P, that it also induces other errors, while in E it doesn't. But so what we see here, so the fact that we can detect, if we compare this to this, if we can detect erasures very well, then the behavior goes from the blue to the red. Okay? And if we have to take into account measurement errors and all, then basically this is what happens. So it's still quite a significant. Okay. So now if you plug numbers, suppose we assume that T1 is 100 microseconds, T gate is around 200 nanoseconds, T measurement, suppose it's kind of long, can take like 400 nanoseconds in many superconducting. And this more is the typical number of measurements. Sometimes people reach faster, but this more is the number. So we get that the erasure error is 0.5%. And you see in this, if you go back to this graph, 0.5% here almost doesn't touch the threshold. So it reduces it from 0.7% to, I don't know what, a bit less than this. So in principle, with these numbers, if you can detect the erasures very well, it almost doesn't have any effect on the code, and we are only limited by T phi. I showed before, T phi can be extremely long. So it means that instead, basically, what we can just plug in this formula of the surface code, P threshold, which is limited by T phi. So T gate divided by T phi. Okay, of course, measurement error can limit the scheme. And what happens is that if there is a false negative, which can be quite bad, suppose if there is an error and we didn't manage to detect it, so in principle, it becomes a Pauli error. But then it will be immediately detected in the next. If you didn't manage to detect it in the first one, we'll definitely be able to detect it in the second one. That's already goes, there's already a very small chance for this. And it will probably not change things so much. If there is false positive, then it becomes an erasure. Okay, and whatever it is, but we can still, so we can, depends what the erasure, what the measurement error is, it becomes an erasure error. So we can, I don't know, maybe it's 1%, we're still quite fine here. We didn't pay such a high price. Okay, there were also, I would like to mention this paper. There was also kind of a similar paper about, not about superconducting, but about erasures for the Rydberg. For the Rydberg atoms, that was before our paper. Kind of the concept is kind of strongly connected. But maybe if you've seen in these graphs, which I show here, these actually numbers are taken for a patent application, which we submitted, was actually quite before that paper. So it was done, our work was done independently. And with this, I think I'm exactly on time. I will thank you for your attention.
Thank you very much, Alex. Thanks and congratulations for the great work. We have made questions already, but we have times for questions, especially if they come from junior people. We always like to start. Don't be shy.
So yeah, my question would be about the decoherence-free subspace. So first of all, how does it play a role in this in the implementation here?
Yeah, so
And because typically, I would guess you decouple it from decoherence channels, right? So this is the concept of these decoherence-free subspaces. But then it kind of relies on the symmetry of the states that are created within this, and they are like, one of them has a like symmetry, and the other one is anti-symmetric, like with the minus sign. So I would expect that one actually couples stronger to that decoherence channel, and the other one less. So I did not fully understand then what is really this decoherence-free subspace. Is it only one of the states? Or is it the one that is actually like those two together or something?
So usually when you have a transmon which is coupled to Wheeler resonator, it's coupled dispersively. So in the end, the coupling is like a ZZ interaction. More specifically, it's a coupling between the states, and C dagger C, it kind of changes the frequency of the Reader resonator at first order. There are corrections which create problems, but in first order, in leading order, it is the transmon changes the frequency of the Reader resonator depending on the frequency of the transmon. So the operator Z of the transmon is coupled to the A dagger A of the Reader resonator. But what couples is the Z. So if you think about the coherence-free subspace, right? If there is noise in Z, the noise in Z will not decohere this qubit, right? That's exactly the decoherence-free subspace, right? Because it will have the same effect on this and in this. So it will give us an overall phase, but will not decohere this qubit. Okay. So in the same sense, this Reader resonator, because it's coupled to Z, it cannot distinguish between this and that, right? It will, all of the terms here will give them the same effect.
So the the subspace of dress states over there is decoherence free with respect to Z noise.
Yeah,
right?
with respect to that noise. And because the Reader resonator at leading order is coupled with the Z operator, so it will have the same effect. It cannot decohere or measure this the qubit plus minus.
Any other question, Sergi?
So you use this resonator to measure if it's still in the computational stage or some decay has happened. How do you distinguish between the computational states then? You do some Bell measurements?
So you can, right. Yeah. So what I can do when I want to do a measurement in the computational subspace, I can make a mapping between this state and this state, or
And
this state and this state, and then make the measurement.
Okay.
And the mapping is quite simple. You just have to drive both transmons at the same Rabi frequency, and you just couple this.
Sure.
Yeah.
Probably I lost some points. Do I correctly understand that you avoid the phase error not by dynamical decoupling because it's not compatible with surface code, but using the decoherence-free subspaces? Is it true, or you do use both?
So it's more both. Is the coupling between the two transmons in this subspace of 0, 1, and 1, 0, it acts like dynamical decoupling. And it's true, dynamical decoupling is not compatible with the surface code in terms of using the code as it is, but it is compatible with erasure errors. That's why I have to use this erasure, because when it's erasure, I mean, if it was compatible, if we could use the 4-qubit codes, we could have get much better results. Mm-hmm. But we can still, if we use an erasure, it's working somehow. We still get an advantage. Yeah. Not as good as if the 4-qubit code would have worked, but still get a disadvantage here.
Mm-hmm. Okay, thank you.
Any other question from the?
Yeah. So your model that you're using, does it take the full circuit Hamiltonian, or do you do kind of like approximations like quantum optics, rotating wave and so on? Because your driving is also quite fast, right? So if it's 100 megahertz, and does this lead actually to errors in the simulation?
So it's
Or maybe also do you plan to expand the simulation to
So-
kind of to going to the full, like to a non-approximated version?
so in numerics we did with the gates, it's everything was taken into account, and we can somehow. So what happens here is that if we think about the non-rotating terms, so this is like 1 megahertz in compared to 5 gigahertz. And it goes square. This is still better, it's like on the order of 10 to the minus 5. But now, if we take into account the Bloch-Sigert shift that we get from the, so then we end up only with higher order corrections. And yeah, I don't remember, but it is already an effect which is smaller than 10 to the minus 6. I don't remember the exact, but it's smaller.
So I have one last question. So this is very nice. So the first level of concatenation, when you correct for erasure noise, you explain clearly how this doesn't decohere the superposition. That's nice. But then, sorry, what's the correction? This was the part that was not clear to me. What is the actual correction operation that you
So the actual
that you
correction
apply there?
operation is the same, is basically the same as is done for the surface code, but when you take into account erasures. So I mean, suppose in this example in which you had like, the parity was odd here and the parity was odd here. If you just use the regular surface code, you will make the correction of this qubit and this qubit, which is the wrong one, and you will end up with a failure. But here, if you correct, if you know erasures, you know that the correction was here, here, and here, you correct those and you correct the state. And if you make these simulations, this is the only thing that was done. If you make the simulation and take into account the statistics, then you will get this better result.
I see.
The threshold goes from like 0.7% to around 5%.
I see. So then the correction only acts on the second level of concatenation on the surface code. I see. The
Mhm.
first one is just to detect where the errors happen, but the actual correction comes. That's a very nice feature.
That's correct.
All right.
And the
I see.
numerics was done on the higher level of concatenation. That's right.
And last question, sorry. Have you put numbers? So for kind of, I don't know, some target algorithm, say, maybe not sure, but I don't know, have you plug this? You showed some numbers here, but like, I don't know, when at some point Fernando was showing last year the CAD codes and concatenated also with surface code, and then he was estimating like the number of total physical qubits that you need for, let's say, running short to break the RSA code. Like, have you made those kind of estimations?
But it's if now Google already showed an experiment in which they kind of reached the sub-threshold behavior, so they're around like 0.6% maybe. So if it works and so here we can improve it by at least order of magnitude, we believe, maybe even more. So it means that we are already at like 0.05% or even less, maybe 0.01%. So I mean, we can just plug these numbers and see, but we are already kind of deep inside the fault tolerance, deep inside the threshold.
Nice. Right. So I guess that's already quite a session, and I would like to thank the speaker again for the nice talk, and congratulations again. Thank you.
Thank you.